All right, so good morning. Again, I have the do now presented up on the screen. So take a look at the do now questions. Number one, I gave you data using the method of initial rates. You need to figure out what the rate law is, so you have to figure out what's the order of each reactant. And then number two is just asking a question about finding the slope of a line. So if you have points on a line, how do you find the slope? As you are looking at the do now, I'm going to shift over to the document camera. So we're going to be going back and forth between the Google slide deck that's presented right now and the document camera. So I'll kind of be flipping back and forth with that as we're going through everything for today. All right, so for the do now, number one says the initial rate data in the table was obtained for the reaction, and it says that there was a reaction represented below, but it doesn't actually matter what the reaction is, because remember that you don't need a balanced equation in order to figure out the rate law. You just need the data. So based on this data, and I wrote it on a piece of paper so that we can work through it, based on this data, I just want to know what the rate law is. So remember that the rate law is always rate equals K times the concentration of reactants. But we need to figure out what power these reactants are raised to. So let's start by looking at NO. So we need to look at how changing NO's concentration affects the rate. So if I look, I want to change only one reactant at a time. So I want to see where NO changes, O2 stays constant, and that's between 1 and 2. So NO changes, goes from 0.1 to 0.2, so it doubles. When NO doubles, the rate goes from 2.5 times 10 to the negative fourth to 5 times 10 to the negative fourth. It also doubles. So if whatever we do to the concentration of NO, the exact same thing is done to the rate, that's first order. So we know that NO is first order. So we're just going to have times the concentration of NO, because it's raised to the first power, which is just NO itself. Then we look at O2. So I want to see, where does O2 change, but NO stays constant? So I initially see, well, from 1 to 3 it changes, but NO isn't constant. From 2 to 3, O2 changes and NO remains constant. So from 2 to 3, we go from 0.1 to 0.4. So 0.1 to 0.4, we're actually multiplying by 4. And if you are stuck and you're trying to figure out what that factor is, on your calculator, just do 0.4 divided by 0.1, right? And it's a 4. So that means that from 0.1 to 0.4, we multiply by 4, which means I want to see what happens to the rate. Now, there's a couple ways you could do trial and error. So you could do 5e negative 4 times 4. That would tell us that it's first order, but it's not. Or you can divide. So 8e negative 3 divided by 5e negative 4, that's 16. So 5 times 10 to the negative fourth times 16 gives us 8 times 10 to the negative third. So when I quadruple the concentration, I multiply the rate by 16. So if this were 0 order, if I quadrupled the concentration, nothing would happen to the rate. If this were first order, I quadruple the concentration, I would quadruple the rate. But I quadruple the concentration, and that squared, 4 squared is 16, that's what happens to the rate. That tells me that O2 is second order. So the rate law is rate equals K times the concentration of NO times the concentration of O2 squared. So that's the rate law. And then number 2 said, from a graph, how do you calculate the slope of a line? So when you have a line, let's say you have a graph, right? You plot the points on a line, looks like this, right? And you have multiple points on this line. I just want to know how you calculate the slope. So remember that slope, the most basic way to calculate slope is rise over run. Well, remember that rise is your y-axis, run is your x-axis. So we're going to do the change in y over the change in x. And even more specifically, y2 minus y1 over x2 minus x1. So if we want to calculate the slope of a line, we pick 2 points. And when we pick 2 points, we do y2 minus y1 over x2 minus x1. The reason that I had you write this down is because this is going to be useful for today. We're going to be calculating slope of a line today. All right, so as we are going through everything today, you will need your notes. You will need your equation sheet. So I know we haven't used our equation sheet in a while, but you will want your equation sheet and a calculator. Now, I recommend using a calculator and not just using your phone, because your phone is going to be more difficult to do some of the computations with. We're going to be looking at natural log, the inverse of natural log. We'll be looking at all of that today. And so you will want to make sure that you have your notes, your equation sheet, and a calculator, preferably not your phone, so that you can practice using that like we would on a quiz or on a test. So during class today, we're going to start by going through questions from the video from last night, so video 5.3, and looking at the summary table in page 12 of the notes. So the summary table is just a way to kind of bring everything from the video together into one place. Then we're going to be doing examples 12 through 18 in the notes. So it's pages 12 to 14. You will want a calculator. And then hopefully there's a little bit of time to work on mastering. We're going to focus on numbers 20 through 35. Those are not all for points. Some are extra credit, some are practice, and then some are regular points. For tomorrow, though, I do want you to watch video 5.4. So this is more conceptual. We're kind of moving back into the more conceptual ideas of kinetics. It is already up in Google Classroom. It's up in Edpuzzle. So just make sure that you have it watched tomorrow by the beginning of class. So as we're going through everything today, I do just want to point out, since we will be switching back and forth between Google Slides and the document camera, if you do have questions and you type it in the chat and I don't necessarily see it and it's been a couple minutes and I haven't seen it, if you send a remind, it'll buzz on my wrist. I can, answer a question that way as well. Sometimes when I'm presenting on the document camera and I flip back over to Google Meet, the document camera kind of flashes. And so if you just want to send questions on remind, you can. But don't hesitate to ask questions as we're going through examples today, especially because all of this is new material. So to go back and review different types of rate laws. So the video last night talked about a new type of rate law. So we looked at differential rate laws. So we just call those rate laws. That's when we look at concentration versus rate. So that's what we wrote in the do now. Rate equals K times the concentration of reactants. This is determined experimentally from data, just like we had in the do now with those method of initial rates. And then we figure out what's the order. That's how we write the rate law. So whenever you see write the rate law, write the experimental rate law, that just wants rate equals K times your concentration. Then in the video last night, I talked about integrated rate laws. Now, you don't need to know how to calculate one over the other. You don't need to know the calculus behind it when you're looking at derivatives versus integrals. Calculus is not part of this. I used to do more calculus, but I'm kind of pushing that to the side for now. So integrated rate laws are allowing us to look at concentration versus time. So notice the difference. concentration versus rate, and concentration versus time. So in order to use these integrated rate laws, we have to know the order of the reaction. So either they give it to us or we figure it out. The integrated rate laws are on the equation sheet. All three of them are on the equation sheet. And something else that we're going to look at today is we're going to look at how to use the graphs of concentration versus time to determine the order of a reaction, whether it's zero, first, or second order. The main difference between these two is that integrated rate laws include time. Differential rate law is rate and concentration. So when we're looking at examples, you want to determine what you have in the problem to figure out what type of rate law is needed. So if the problem is talking about time, minutes, seconds, that means we're going to be using the integrated rate law. If it gives us a set of data, like in the do now, then we're going to just be writing rate equals K times concentration of reactants. So when you look on your equation sheet, on the bottom of the first page, so on the bottom of the front of your equation sheet, it says kinetics, and it looks just like this. I just took a screenshot of the equation sheet. So these first three equations, these are your integrated rate laws. So you have zero order, first order, and second order. You have them written down for you already. So make sure that you know concentration is zero order, ln of concentration is first order, 1 over concentration is second order, and then you're also given the half-life equation for a first order reaction. So what we're going to do next is we're going to go ahead and summarize integrated rate laws into the table that's at the top of page 12 of your notes. And so in this table, we'll look at what's the integrated rate law, what's the graph that gives us a straight line, what's the slope, what's the half-life. And as we look at this, something that's important to remember, and I put a star right here. So before we even start filling everything out, the star is for the first order half-life. The only half-life that you are tested on is first order. So the only types of questions about half-life that you will see will deal with a first order process. And that's because, and this that's at the bottom of this slide, this is already in your notes. I typed this exact thing out. I just copied and pasted it right from your notes. The only reason that the first order is so important is because it's independent of concentration. Doesn't matter what your concentration is. The half-life is constant. Unless you change temperature, half-life is constant. That's how you know that it's first order. And we'll talk more about that as we look at half-life. So I'm going to go ahead, I'm going to switch back to the document camera, and we're going to go ahead and we're going to look at the summary table for integrated rate laws. So we're going to go ahead and take a look at, right, so again, this is at the top of page 12. We're going to look at each order individually. So we're going to look at zero order, then first order, then second order. And as we go through this, what I'm hoping is that we can kind of put everything together. You know how to tell that something is zero or first or second order. Before we get into the integrated rate law, what I want to do up here at the very top is I just want to write the rate law. So if it's a zero order process, let's say that we're looking at the reaction A yields B. If it's zero order, if A is zero order, the rate law is just rate equals K. Right? The rate law is just rate equals K because A to the 0 is 1. So if it's a zero order reaction, the rate law is just rate equals K. Now the integrated rate law, this is on your equation sheet. I'm going to write it a little bit differently than how it looks on your equation sheet, but it is the same thing. I'll show you why I'm writing it like I am when we talk about the graphs. So the integrated rate law for a zero order reaction is the concentration of A after some time equals negative K times T plus the initial concentration. So brackets represent concentration. So when you see the brackets, that means concentration. This sub T, this means the concentration after some time. K is rate constant, T is time. Concentration sub 0, that means initial, that's at time 0. So this is the integrated rate law for a zero order reaction. The graph that gives you a straight line. So if it's zero order, concentration versus time will give you a straight line. It's going to look like this, right? Concentration versus time is going to be a straight line. And this could be concentration of A or B or whatever your reactant is. Concentration versus time will give you a straight line. The slope of this line, the reason I wrote this equation, the integrated rate law, like this, is because this looks like y equals mx plus b. Again, y equals mx plus b. Well, m is the slope. The slope equals negative k, because this line has a negative slope. So when I solve for slope, it's going to be a negative number. To make sure that the rate constant is always a positive number, I have to put a negative in front. All right, so again, I'm going to just write this over here. Rate constant is always positive. So remember that if you're solving for the slope, you're solving for the rate constant, and you get a negative number, put a negative in front of it, make it positive. K is always a positive number. Now, half-life. I don't usually give the zero order half-life equation, but some people are asking about it. That's why it's actually grayed out. But people were asking about it. So first, half-life, the definition of half-life. So the definition of half-life is how long it takes to get to half of the original sample. Okay, how long it takes to get to half of the original sample. So let's, just an example, right? I love those little, what is it, Haribo gummy bears. So the half-life is the time it takes for me to eat half of those gummy bears. Time it takes to get to half of the original amount. Could be an hour, could be 10 minutes. So half-life is how long it takes to get to half of the original sample. The shorter the half-life, the faster the reaction. So if I can eat half of a bag of gummy bears in 5 minutes, that's a fast reaction. And then I eat half of those in another 5 minutes. Right? That's the half-life. The shorter the half-life, the faster the reaction. Now, the half-life equation for a zero order reaction is the initial concentration divided by 2 times the rate constant. Now, I'm going to put a star in each of these because the star indicates that these are not tested, right? I am not testing zero and second order half-life equations. I'm only going to focus on the first order. Okay, so that's zero order. You can tell something is zero order if the concentration versus time graph gives you a straight line. Then we can look at first order. So if this process, right, A yields B is first order. If A is first order, the rate law is rate equals K times the concentration of A. Right, it's first order. Exponent is 1. While the integrated rate law, and again, this is on your equation sheet, is the natural log of A after some time equals negative KT plus ln concentration initial. Again, I manipulated the equation to make it look like the equation of a line. On your equation sheet, it's ln of A sub t minus ln of A initial equals negative KT. It's the same thing. ln is just a mathematical process. So natural log on your equation sheet, natural log is first order. So the graph that produces a straight line is the natural log of concentration versus time. So natural log of concentration versus time. We have a graph, right? ln of concentration. The brackets just represent concentration. Graph's going to look like this. If it's a straight line, that means it's first order. Right? If ln versus time gives us a straight line, it's a first order process. The slope, just like zero order, the slope, because it's negative slope, the slope equals negative k. Notice how that matches right here. Now the half-life, this is the important one. Right? This is the important one. Half-life of a first order process is 0.693 over k. This is on the equation sheet. This is on your equation sheet, 0.693 over k. 0.693 is actually the natural log of 2. Something that's important is that the half-life is constant for a first order process. That means that it remains the same. So to get from my initial to half, let's say that's 10 minutes. Well, then if going from the next sample to half of that is 10 minutes, the next sample to half of that is 10 minutes. That means that it's a constant half-life. That tells you that it's first order. 0 and second order are not constant because it depends on the concentration that you're starting with. So my process of eating my gummy bears is probably not first order. It's not going to be constant. Right? If it takes me 10 minutes to eat half of the bag initially, it's probably going to take me a different amount of time to eat half of what's left and to eat half of what's left. That's not a constant half-life. Okay, so this first order process, this is what's important. This is what you're going to be seeing most questions on, is the first order process. So finally, second order. So if we write the rate law of a second order process, it would be rate equals k times the concentration of A squared, right? 2 for second order. Well, a second order process, the integrated rate law, is 1 over the concentration of A after some time equals k times T plus 1 over the initial concentration. So I'm writing all of these integrated rate laws so that they look like the equation of the line. So the third equation down on your equation sheet, that's a second order process. Well, if you tell, based on what we've done so far, right, look at the integrated rate law for each order and look at the graph that gives us a straight line. 1 over concentration versus time gives us a straight line if it's second order, right? Only if it's a second order process. Now this gives us a positive slope, which means the slope is just equal to k, right? It's our rate constant. And then again, the half-life equation, so half-life of second order is not tested, but the equation is 1 over k times the initial concentration. So notice how 0 and second order both depend on concentration. That's why they're not constant. First order does not have concentration anywhere in it. Okay, so that's looking at the summary table. So this kind of summarized everything from the video into one table. We even got the graphs drawn in as well. As we shift back over to the slides, just really quick, if you have any questions, feel free to type them into the chat. I'm going to just switch back over so that way we can look at the graphs. I actually took a screenshot from, like I kind of just made a summary and put the picture right into the slides. So if we take a look at the slide deck, and again, before we go to the graphs, I just want to point out at the bottom again about half-life. So College Board likes to ask questions about the half-life of a first order process because it does not depend on concentration. Instead, it's constant throughout the reaction. So if the half-life is 10 minutes at the beginning of the reaction, it's going to be 10 minutes at the end of the reaction. That's how you can tell that it's first order. They also like to ask questions on radioactive decay. So nuclear chemistry. Anytime you have radioactive decay, that's first order. So the half-life will remain constant. So if we take a look again, here are the graphs. So here are all three graphs, 0, first, second order. If it's 0, if it's a 0 order process, concentration versus time results in a straight line. This is your integrated rate law from the equation sheet. So notice in the summary table, I just moved this minus, I added it to the other side. First order, ln versus time results in a straight line. You have the integrated rate law. Second order, 1 over concentration versus time results in a straight line. Now your units for K. So K is a rate constant. Notice how your units for the y-axis are different in every graph. And so here you just have molarity. The natural log gets rid of units, so there are no units for that. And then 1 over concentration would be per molar, because it's 1 over molarity. And so that's how we can actually get our different units for the rate constant. So notice how that still matches up with what we've been looking at already. So what we're going to do next is we're going to go ahead and jump into the examples. So the example 12 will be the first example that we look at. Example 12 is right underneath the summary table. And so we'll go into example 12. We'll look at how to solve these examples. Some of them I might have you kind of do some on your own. We'll come back together. So right underneath the summary table, we have example 12. And example 12 is actually part of kind of an older free response question where you had to actually graph data. Now, the data that you graph, they already gave you the scales of each of the graphs at the bottom of the screen. So if we look at example 12, it says the following represents data from a reaction. Fill in the missing data in the table. Then plot the data onto the 3 graphs, calculate the slope of the straight line that was generated, and include units. So 2 things that we're going to do first. We'll worry about the slope at the end. 2 things we're going to do first. 1, we need to figure out what's the natural log of concentration, right? So here's concentration. We need to figure out what's the natural log of concentration. We're going to put all of those values here. What is 1 over concentration? So 1 divided by all of these concentration units. Those go here. So here's what this will look like. I want to take natural log of the concentration of A. So ln of 10, 2.30. That's what I'm going to fill in. All right, and I'm going to work all the way down. So I'm going to work all the way down for natural log, and then I'm going to do the same thing for 1 over. Now 1 over concentration, it's not 1 over ln, it's 1 over concentration. So 1 divided by 10 is 0.1. So I'm going to go ahead. I want you to do the same thing. So I want you to use your calculator. This is why I said use your calculator. It's going to make it easier. Use your calculator and do ln of concentration. Put them in the table. 1 over concentration. Put it in the table. And then see if you can graph each of them. So once you have it in the table, you're going to graph concentration versus time. So here's my X and my Y. Then it wants ln concentration versus time. So time is my X, ln is my Y. Then 1 over versus time. Time is my X, 1 over concentration is my Y. So there are your points that you'll be using to graph. So fill in the table and then graph each one. And I'll be working through it up here as well. So if you want to check your table with mine, I have mine filled in. So again, I just did ln of concentration, filled it in, 1 over concentration, filled it in. And now, could you do this like on a computer? Yeah, but you can't do that on the AP test, right? Like this is what the AP test looked like. So you had to actually graph, and you'll notice that they gave you the scales to actually make it easier to graph. So once you have your table filled in, you can go ahead and you can graph everything as well. So for concentration versus time, at time 0 was 10 molar. And you just want to estimate if it's not exactly. And once you have your graph, it might help to connect the lines. Don't force a straight line either. Just connect the dots. Then I'll do the same thing for natural log. Nine. And I'm actually just going to round as much as I can. Okay, so I just went through, I found everything in the table, and then I also graphed all 3. So I'm going to use a highlighter, and I'm going to actually highlight my lines just to make it easier for you guys to see. And so I tried to connect my points the best I could. Okay, so there are my lines. Now, this says calculate the slope of the straight line. So the whole point of this was first to look at what order could this be, right? All they gave me was that I had concentration of A versus time. Well, I can figure out the order based on what we did up here at the top, right? If I look at my summary, whichever graph produces a straight line or the straightest line, that tells me the order of the reaction. So if I take a look at what I did down here, if I take a look at what I did, I have all 3 graphs here. Now you always want to pick the straightest line. So here I have, that's concentration versus time is for sure curved, right? So not straight. And so that means that it's not 0 order, right? Not 0 order, because if concentration versus time was a straight line, it would be a 0 order reaction. Now, we're looking between natural log and 1 over. You want to pick the straightest line. I noticed down here towards the bottom, it starts to curve, right? I noticed that it starts to curve. The 1 over concentration, that's a straight line. Right, so this is my straightest line. And so what I'm going to write down here at the bottom, and then I'll figure out the slope, is because 1 over concentration versus time gives a straight line. This reaction is second order. So since we know that 1 over concentration versus time gives us the straightest line, we would say that this reaction is second order. And we could do other information from that, but we know that this is second order. Now it says, calculate the slope of the straight line that was generated and include units in your answer. So I am calculating the slope of my 1 over concentration graph. Right, so I want to pick points from the straight line. I'm not going to pick points from one that's curved. I need to use my 1 over concentration information to find the slope. Now, you might look at this and you're like, okay, well, should I just pick points from here? Yeah, you can. But what happens if your scales are difficult to read or it's hard to estimate? Well, look up here. Here are your points. There's your point. Y, X, Y, X. So to calculate the slope, right, pick 2 points and do change in Y over change in X. Y2 minus Y1 over X2 minus X1. So my 2 points, I always pick the first and the last point, because then it kind of covers everything in between. So Y is your 1 over values, 1 over concentration values. So I'm going to do 0.40 minus 0.10. And my units, because it's 1 over concentration, is per molar over X2 minus X1. So that's 60 minus 0 seconds. Right, because it's Y over X. Now, here's what I did, here was Y2, X2, Y1, X1. I didn't even worry about concentration or ln because those weren't straight. Those aren't straight lines. So I'm going to go ahead and just calculate my slope. 0.4 minus 0.1 is 0.3, divided by 60 minus 0 is 60, 0.005. And then my units are per molar, m to the minus 1, per molar per second. Remember that per seconds is also s to the minus 1. And if you look back at the review that we did yesterday, if it's a second order process, your units for your rate constant are per molar per second. So this is just looking at being able to graph data and figuring out what is our straight line, right? What does that mean about order? Okay. Any questions on this example? Right, so we're going to go ahead and we're going to go to example 13. So example 13 is on the next page up at the top, and 13 and 14 are similar. 13 and 14 are actually similar to a couple mastering questions as well. So just make sure when you're working through mastering, if you see questions like this, just remember you can flip back. So example 13 says the first order rate constant for the decomposition of a certain insecticide in water is 1.45 per years. Okay, so I'm gonna pause really quick. There's a couple things that are important here. It says that it's first order, right? So they're telling us the order. And the first order rate constant is 1.45 per year. So that's K. So first order rate constant is 1.45 per year. So notice the units are a little different. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5 times 10 to the negative 7th grams per centimeter cubed. Assume that the effective temperature of the lake is 12 degrees Celsius. So the reason that they say the effective temperature is 12 degrees is assume that the temperature isn't changing. Because if the temperature changes, the rate constant changes. So if I look at what I have here, because remember we have to figure out what are we using, how are we solving. So if we look at what we have in the problem, because we want to determine what we have in the problem to figure out how to solve. If it asks for an experimental rate law, then we need to know what's the rate and concentration. We need that data, like in the do now. If they give us concentration and time, we'll use the integrated rate laws from the equation sheet. So if I take a look at this, it wants to know what is the concentration on June 1st of the following year. So this is concentration and time, which means I'm going to be using the integrated rate law. So integrated rate laws are on the equation sheet. You have to figure out which one. Is it 0, first, or second order? Well, that's why this was so important that they told us this at the beginning. It's first order. So if you look at your equation sheet, remember that the first order integrated rate law is the natural log of the concentration of A after some time minus the natural log of the concentration of A initially equals negative K times T. So we're dealing with natural logs here. And when we're looking at concentration, our goal is to solve for concentration after some time. So this is the variable that we're going to be solving for at the end, which means we should have everything else. Now it says June 1st of the following year. So it got put in on June 1st. We're looking at June 1st of the following year, which means the time, T, is 1 year. Now I'm going to zoom in a little bit because we're going to be working with natural logs here. So I'm going to plug in what I know. So I know nothing about concentration after some time. I'm going to leave that alone. That's what I'm solving for. Minus the natural log of the initial concentration. Right? So the initial concentration is 5 times 10 to the negative 7th grams per centimeter cubed equals negative K. They gave us the rate constant, 1.45 per year. And the time they gave us was 1 year. Now you need to make sure when you're plugging things into your integrated rate law that whatever your units of your rate constant are, your units of time match up with that so that they cancel. Per year means 1 over year. So per year times year will cancel out. That's what you want. So now I have everything that I need to solve. So I'm going to start by rearranging this equation for ln of A sub t. So I'm going to move it up here. So ln of A sub t, right, the natural log of concentration after some time, equals, I'm just going to go ahead and multiply these right now. Negative 1.45 times 1 is negative 1.45. And I'm going to add this. Notice how it's minus ln of 5 times 10 to the negative 7th. So I'm going to add ln 5 times 10 to the negative 7th to the other side. So I'm going to do negative 1.45 plus natural log. So natural log is the third button from the bottom, right? Natural log is right here. Not log, but natural log, ln. So negative 1.45 plus ln 5e negative 7 Negative 15.96. So the natural log of the concentration of A after some time equals negative 15.96. Now to solve for the concentration, if I just try to do divided by ln, enter, it's an error. Can't just divide by ln. Natural log is a function. To get rid of natural log, you have to use the inverse log. If you look on your calculator, natural log, right above it, you have e to the x. That is the inverse log. So the inverse log, if I do e to the ln a, I have to do it to the other side, e to the negative 15.96. And when I do that, e to the ln cancels. And I get the concentration of A after some time. In your calculator, you have to hit second ln so that it looks like this. This is different from the exponent button. I'm going to do negative 15.96. 1.17 times 10 to the negative 7th. Now, brackets means concentration. Use the same concentration units that they gave you. Make sure your concentration units are the same. So in the top of the problem, they gave us 5 times 10 to the negative 7 grams per centimeter cubed. So 1.17 times 10 to the negative 7 grams per centimeter cubed. The biggest thing is solving for a variable with natural log. You're using the inverse log, right? E to the ln. So just in case you forget, haven't seen it, the e, the lowercase e, is how you can, that's your inverse log. That's how you can get rid of it. Okay, so then part B of this says how long for the concentration of the insecticide to drop to 3 times 10 to the negative 7th. So how long? How long means time. Right? How long means you're solving for time. And they're giving you another concentration. So remember, everything up at the top still applies. Right? All of this information up here at the top still applies. It's still first order. You still have the same rate constant. You still have an initial concentration. Now I'm solving for time. So it's still first order. So ln of concentration A after some time minus ln of the initial concentration equals negative k times t. So let's plug in what we know. The natural log, so the concentration after some time is 3 times 10 to the negative 7th. Minus the natural log of the initial concentration, that's 5 times 10 to the negative 7th. Equals negative, don't forget your negatives here. So negative k, 1.45 per year times t. You're solving for time. Now remember that your time unit will match up with your rate constant. So t will be in years. Time should be days, seconds, hours, minutes, years. That's time. So if I solve, here's what it will look like in my calculator. ln of 3 e negative 7 minus ln of 5 e negative 7 equals. So now to get t on a side by itself, I'm going to divide by negative 1.45. So t, time, 0.35 years. 0.35 years. So this is where we're looking at integrated rate laws. You're using concentration versus time. Any questions on example 13? All right, so let's go on to 14. So again, if you want to make yourself a note, 13 and 14 are questions similar to mastering, in which you're using integrated rate law. So example 14, decomposition of sulfurochloride is a first order process. So again, they tell us this is a first order process. That's important. The rate constant for the decomposition is 4.5 times 10 to the negative second per second. So this is K. It's rate constant. A says, if we begin with an initial pressure of 375 torr, what is the pressure of this substance after 65 seconds? So you might look at this and say, all right, well, we were dealing with concentration before, now we have pressure. Why do we have pressure? Well, pressure can be substituted in for concentration. Right? So pressure can be used instead of concentration. That's okay. Because gases are typically measured in pressure instead of concentration. So that's all right. So if we begin with an initial pressure, so here is P initial. What's the pressure after 65 seconds? So here's my time. I'm solving for the pressure after some time. I'm dealing with pressure versus time, integrated rate law. First order, meaning we're using ln of pressure after some time minus ln of pressure initial equals negative K times T. You say, well, where did I get that from? Well, I used it from the equation sheet, but instead of concentration after some time and initial concentration, I just plugged pressure in. So let's plug in what we know. What's the pressure after 65 seconds? So I'm solving for pressure after some time. Initial pressure is 375 torr. K is 4.5 times 10 to the negative second. And time is 65 seconds. So notice how K is in per seconds, time is in seconds. That's good. If time wasn't in seconds, you would want to convert it to seconds. So I'm going to go ahead and I'm going to rearrange this equation right now. All right, so I'll move it up here. ln of P after some time equals negative 4.5 times 10 to the negative second times 65 plus ln of 375. So I just rearranged it to get the pressure variable on a side by itself. It's minus ln, so I'm just adding it to the other side. So in my calculator, I'll go ahead and do negative 4.5 e negative 2 times 65 plus ln of 375. So the natural log of pressure after some time is 3.00. Again, that's not our answer. We have to get pressure, not natural log of pressure. So I'm going to do e to the ln equals e to the third. That gets rid of this. So in your calculator, hit second ln. You get 20.1. This is pressure. Pay attention to what variable you're solving for, what your units are. P is pressure. Pressure was given in torr. Pressure will end in torr. Right, 20.1. And then part B says, at what time will the pressure decline to 1/10 of its initial value? So when will it decline to 1/10 of its initial value? Well, P initial was 375 torr. So 1/10 of that divided by 10 is 37.5 torr. Again, all I did right now is I said, okay, initially it was 375. That's what they told us in the problem. We want 1/10 of its initial value. That's 37.5. And it says at what time? So I'm solving for time now. It's still first order. So I'm going to go ahead and do ln of 37.5 minus ln of 375 equals negative k times t. Right? I'm using the integrated rate law. I'm using this integrated rate law from before I just plugged in. Pressure after some time is 37.5. It's 1/10 of its initial value. Initial is 375. K is 4.5 times 10 to the negative second. So ln of 37.5 minus ln of 375. To get t by itself, I need to divide by negative 4.5 e negative 2. And I get 51.2. So t is 51.2. Now look at your units for k. K was per seconds, which means time should be in seconds. The time will be in seconds. All right, any questions on 14? These were probably the two longest ones because these are questions similar to mastering. So the next few we'll go through more quickly. I know you're probably like, oh, thank God. So example 15, this actually is an old AP question. So it says the radioactivity of a sample of iodine 131 was measured. So radioactivity is important because it's talking about a radioactive process. So it's talking about radioactive decay. So radioactive decay is an example of a first order process. Right, so again, radioactive decay is an example of a first order process. College Board likes to ask questions on radioactive decay. So the data collected was plotted on the graph. A says determine the half-life, T1/2, using the graph to the right. So remember that half-life, so half-life is the time it takes for a sample to get to half of its original amount. So the half-life of a substance is the time it takes for a sample to decay to half of its original amount. So if I take a look at this graph off to the right. So here's my graph. Here's the amount that I have initially. At time 0, I'm starting with 16,000. So think of half of 16,000 is 8,000. So I'm going to follow 8,000 to the curve. I'm going to follow it down to time. 8 days. Right? So to get to half of the original amount was 8 days. So my answer to part A was 8 days. Now, here's how we can tell if it's first order. This is going to help us answer part B. A first order process has a constant half-life. So what that means is, now let's look at 8,000. To get to half of 8,000 is 4,000. I'm going to follow 4,000 over to the curve and go down. Well, 8,000 was at 8 days, 4,000 was at 16 days. That's another 8-day difference. Let's look again. Half of 4,000 is 2,000. Follow 2,000 all the way over to the curve and down. That's another 8 days. So the half-life is constant. Right, so how does the graph verify that the process is first order? The half-life is constant throughout the process. Since it's constant, that tells us that it's first order. Then part C, using the half-life from the graph, calculate the rate constant with units. So the equation for half-life is T1/2 equals 0.693 over K. That's the equation. That's from the equation sheet. It's first order. We know one of two ways. It's radioactive decay, that's first order. And we also know because it has a constant half-life. So if I plug this in, I'm solving for rate constant. I need to rearrange this for K. I'm going to multiply both sides by K and divide by the half-life. So if I'm solving for the rate constant, it's K equals 0.693 over T1/2. 0.693 is just a number. It's the natural log of 2, so there's no units. The half-life is 8 days. So if in my calculator, I do 0.693 divided by 8, I get 0.0866. Now it says with units. Well, there's nothing over days. So we have per days. Per days is days to the -1. So if you know the half-life, you can find the rate constant. If you know the rate constant, you can find the half-life. That's important. This is a very common type of question that College Board likes to ask. So then part D says the data can be used to show that the decay of iodine 131 is a first order reaction as indicated on the graph. All right, so here's the graph. Label the vertical axis. So we want to label that the y-axis here. So notice that it creates a straight line. So it's something versus time. So if it creates a straight line and you're looking for it to be a first order reaction, you're thinking about what could I put on the y-axis that would create a straight line? Well, you could put natural log of the concentration of iodine 131. Right, so the natural log of iodine 131 is on the y-axis. That gives you a straight line. And then part 2, explain how the half-life can be calculated using the slope of the line plotted on the graph. So when we find the slope of this line, the slope is equal to negative K. Right, the slope of this line is equal to negative K. So we can say the slope of the line will give us the rate constant. So the slope of the line will give us the rate constant, but it wants to know how we can find the half-life. So we can plug the rate constant into the half-life equation. So just like up here, we plugged in the half-life and solved for the rate constant, we could do the same thing. We could plug in the rate constant and solve for the half-life. So this is very much a type of free response question that College Board would ask. Right, so then example 16. So I'm going to give you guys a few minutes for this. So if you need to take a break and get up and move around, you can. So we're going to take about 3 minutes for this. It's probably going to take you much less to answer it and then just do what you need to do. So for this, it gives us an equation. And it says the decomposition of H2O2 is represented by the equation above. A student monitored the decomposition at a constant temperature, recorded the concentration as a function of time. Results are given in the table below. Which of the following statements is a correct interpretation of the data regarding how the order of the reaction can be determined? So I want you to read through the 4 possible answer choices. This is a multiple choice question. Read through the 4 possible answer choices. And then I want you to see if you can pick out the correct answer. And then go ahead and take a few minutes. So in 3 minutes, we'll come back, we'll answer this question, and then we have 2 more examples that we'll go through before you have a little bit of work time. So take about 3 minutes, answer this question, and then take a break if needed. All right, so let's take a look at example 16. We'll talk through why some answer choices are correct and why other ones are not correct. So if we take a look at this, again, this wants to know which of the following is a correct interpretation of the data. So A says the reaction must be first order because there's only one reactant species. Well, it might be first order, but the reason is not because there's only one species, because we always must look at the data. All right, so we must look at the data. So in order to figure out the order, we have to look at the data, and that might mean looking at rate versus concentration, like we did in the do now, or it could mean looking at the graphs like we did in one of the examples. Part B says the reaction is first order if the plot of natural log of concentration of H2O2 versus time is a straight line. Well, that's correct. We know that's correct. Let's see if there are any other ones that are better reasonings. So part C says the reaction is first order if the plot of 1 over concentration versus time is a straight line. Well, that's not true. That's not even correct because it's not first order. If 1 over concentration versus time is a straight line, it would be second order. And then part D, the reaction is second order because 2 is a coefficient. Well, that's not true. Remember, we cannot use coefficients for these, right? We can't rely on the coefficients. We have to rely on the data. So the best answer here is B. So then example 17. So 17 and 18 are going to be looking at what we did in the do now with slope. So the following data was obtained for the decomposition of NO2. They gave us time versus concentration data. And then off to the side, you'll notice that you also have two graphs. You have natural log of concentration of NO2 versus time, and 1 over concentration of NO2 versus time. A says, what is the rate law? So the rate law, remember the rate law is rate equals K times the concentration of your reactants. Well, concentration of my reactant, I know that my reactant is NO2, but I need to figure out what is the exponent going to be. I need to figure out what is the order. So I need to look at the graphs over here to figure out the order of NO2. I'm still using the data to figure out the order of the reaction. So based on these two, the one that's the straightest line is 1 over concentration of NO2 versus time. Straightest line is 1 over concentration versus time. So right underneath here, I'll say since the 1 over concentration of NO2 versus time is a straight line, the reaction is second order. So again, since the 1 over concentration versus time is a straight line, the reaction is second order. That means that I'll have a 2. So rate equals K times the concentration of NO2 squared. Now, part B says, what is the value of K with units? I don't have rate data to plug into the rate law to solve for K like we did before. I don't have rate here. I have time and concentration. But I do know what graph gave us a straight line. If I know what graph gave us a straight line, remember that the slope of the straight line plot gives us K. So the slope of the straight line plot gives us K. The straight line was 1 over concentration of NO2 versus time. So in order to find the rate constant, I need to find the slope of the 1 over concentration versus time graph. I need to find the slope of this graph. So I need to know what are 2 points that I can use to solve for the slope. Now, if you look at this graph, it's really hard to estimate. It's hard to find points. Well, they give us the data over here. So what if I just do 1 over concentration of NO2? 1 over concentration is going to give me the unit of per molar. I don't even need to find it for all of these points. I just want to find the first point and the last point. Because if I find the first point and the last point, that gives me a good idea for the line in between. So 1 divided by 0.01 is 100. So this first data point is 100. 1 divided by 0.0038 is 263.16. So now what I have is here is my Y, right? 263.16, Y2, Y1, X2, X1. So my slope, Y2 minus Y1 over X2 minus X1. So 263.16 minus 100 per molar is the unit on the top, over 300 minus 0 seconds on the bottom. divided by 300. 0.544 per molar per second. .544 per molar per seconds. So use the slope of the straight line plot to give us K. So over here, the slope of whatever the straight line plot is will give us K. So y2 minus y1 over x2 minus x1. If this was a negative number, you just make it positive. For a second order reaction, it will always be positive. Okay, so that's going to be our rate constant. That's K. Now let's look at the same thing for 18. Right, consider the data presented. By using the appropriate graphs, determine whether the reaction is first order or second order. So let's look at the two graphs. We have natural log of concentration of A versus time, 1 over concentration of A versus time. The one that's the straightest line, gives us our order. 1 over concentration versus time is the straight line. And so this reaction is second order. And because we're looking at concentration of A, we can say with respect to A. That means that A is second order. Since we're looking at 1 over concentration of A, we would say that A is second order. If you just said second order, that's fine. So part B says, what is the value of the rate constant for this reaction? So the value of the rate constant, remember, that means that we're looking at the slope of the 1 over concentration of A versus time is K. So the slope of 1 over concentration of A versus time, the slope of this graph over here will give us K. But we need to pick 2 points, right? I need to pick 2 points on the graph. Here's concentration of A, so I'm going to do the same thing I did before. 1 over concentration. 1 over molarity gives me the unit per molar. M to the minus 1 is just 1 over molarity. So 1 divided by 0.65 is 1.538. 1 divided by 0.31 is 3.226. So I notice how I used 0.65 and 0.31. You have to use molarity. They gave us moles and molarity. You have to use molarity. So to find the slope, we'll do y2 minus y1 over x2 minus x1. So y2, 3.226 minus y1, 1.538 per molar over x2 minus x1, 40 minus 0. Notice the unit, minute. Doesn't always have to be in seconds. You just have to make sure that you give the correct units. So 3.226 minus 1.538 divided by 40 is 0.4. Hold on, I forgot a 0 on here. 0.0422 per molar per minute, right? Per molar per minute. And then finally, what is the half-life? Right, so again, remember that second order half-life is not tested. So I'll make a note over here. Second order Half-life is not tested. So I know this is asking about it. You might see questions about it, but it's not tested. So the equation for half-life of a second order process, you need to know first order. Half-life of a second order process is 1 over K times the initial concentration. So 1 over 0.0422 times initial concentration up here is 0.65. So 1 divided by the quantity, 0.0422 times 0.65, 36.5. Right, this rounds to 36.5. T is time. So when you're looking at this, you have per molar per minute times molarity. So those will cancel. 1 over per minute, that's like taking the reciprocal. So time here will be in minutes. It's going to be in the same unit of time that we've been working with in the problem. Okay, so in this, we looked at a lot of different examples, but they all came back to looking at graphs to determine order and using those graphs to calculate the slope. So we'll continue to look at other examples through the do nows. In the videos, we'll continue to come back and look at other ones. We'll do free response questions next week where you see more questions like this. Are there any questions before we finish up for today?